Please subscribe to support the channel. When we look up at the moon, it always seems to show the same face, the same bright plains and dark patches night after night. That simple fact sparks an irresistible question. Why doesn't it ever turn? It moves around Earth, so shouldn't we eventually see its other side? This illusion of stillness has fooled people for centuries, making many believe the moon doesn't spin at all. But the truth is far more intriguing. The moon is moving in a perfectly balanced rhythm, a cosmic dance so precise that it hides its spin from us. The secret isn't that the moon doesn't move, it's that it moves just right to always keep one face turned toward Earth. That constant, familiar face of the moon has quietly built a belief so deep and universal that most of us never think to question it. For centuries, people have looked at the night sky and assumed the same simple conclusion: the moon must not spin. After all, if it were turning, wouldn't we see the other side eventually? The fact that one half of the moon has remained hidden from human eyes for almost all of history seems like irrefutable evidence. We never see the far side. Therefore, the moon doesn't rotate, or so it appears. This assumption feels so logical, so obvious, that it persisted through ancient civilizations, early astronomers, and even into the modern era before science finally untangled the illusion. Think about how powerful that belief must have been. To the earliest skywatchers, the Sumerians, Babylonians, Greeks, Chinese, and countless others, the moon's behavior seemed simple and reliable. It waxed and waned, it marked time and tides, and through it all, its face never shifted. They saw change in its light, but not in its surface. The same craters, the same shapes, the same eyes and mouth pattern appeared generation after generation. And from that unchanging image came myths, stories, and poetic symbolism. The moon became a steadfast companion, a face looking down from the heavens. No one thought of it as spinning because to the human eye, there was no hint of motion. Even today, with all our telescopes and spacecraft, that intuition still clings to us. Ask someone at random, does the moon spin? And you'll often hear a confident no. It's not ignorance, it's perception. The human brain trusts what it sees, and what it sees is a moon that always looks the same. It feels obvious, but that's exactly what makes this topic so fascinating. The truth hides behind what seems self-evident. What appears to be stillness is actually motion. What seems like stability is in fact a perfectly balanced spin. This idea challenges our instincts because our everyday experiences with rotation are completely different. When you see a globe spin, you watch new continents come into view. When Earth rotates, we experience day and night. The changing view of the sun makes the motion undeniable. When a car tire spins, you see a blur. Rotation in our minds means visible change. So when we look at the moon and see no change, we conclude there must be no rotation. It's a natural assumption, but one that misunderstands what spinning really means in space. The moon's motion happens on a much grander scale, synchronized in a way our senses can't easily detect from one short lifetime of watching. It's important to remember that before the age of space exploration, humanity had no direct way to see the moon's hidden hemisphere. The far side, sometimes mistakenly called the dark side, remained completely out of sight. It wasn't until 1959 that the Soviet spacecraft Luna 3 captured the first blurry images of that mysterious terrain, proving that the moon does have another side, a side dramatically different from the one we see. That single moment shattered a belief held for millennia. It forced scientists and the public alike to reconsider what the moon was actually doing up there. The images didn't just reveal new craters and mountains, they revealed the truth about motion itself. But long before space probes confirmed it, mathematicians and astronomers had begun to suspect the moon's hidden movement. In the 17th century, Galileo, Kepler, and later Cassini studied its motion and realized that something subtle was happening. The moon wasn't simply carried around Earth like a dead weight. It was rotating on its axis, just at the right speed to keep one face turned toward us. They recognized the illusion for what it was, a trick of synchronization. Yet even with their discoveries, the public imagination took longer to catch up. It's one thing to write it in a formula, it's another to see it and feel it intuitively. This belief that the moon doesn't spin is also a reminder of how our perceptions can mislead us in cosmic matters. We humans live at a scale where motion is fast and visible. We're used to seeing change within seconds or minutes. The moon, on the other hand, takes more than 27 days to complete one single rotation. That's nearly a month for one spin. To our eyes, watching night after night, that motion is too slow to notice. It's like trying to watch a clock's hour hand move. It's happening, but you'll never see it in the moment. Only when you look back over days or through time-lapse data does the rotation become undeniable. And here's the subtle irony. Very the thing that makes the moon seem stationary, its constant face, is actually proof that it is rotating. If it truly didn't spin, we would see every side of it as it orbited Earth. Over the course of a month, the moon would turn different faces toward us, revealing all of its surface, not just one half. The fact that it doesn't do that means it must be spinning once for every trip it makes around our planet. That's the twist that turns a simple assumption upside down. What seems like stillness is the result of an incredibly precise motion. But to grasp this fully, to move beyond the illusion and see what's really going on, we have to get clear on our definitions. What exactly does it mean when something spins? What's the difference between rotating and revolving? These words might sound interchangeable, but in astronomy, they describe two distinct kinds of motion, and understanding that distinction is the key to unlocking the moon's secret. Once you know the difference, the whole mystery unravels beautifully, like watching the gears of a cosmic clock suddenly fall into place. Before we can truly see through the illusion of the moon's stillness, we have to pause and ask a deceptively simple question. What do we actually mean when we say something spins? It sounds obvious at first, but in the language of astronomy, spinning isn't just about movement. It's about how that movement happens. It's about whether an object turns on itself or simply travels around something else. The confusion over the moon's motion isn't really about what it does, it's about what we mean by the words we use to describe it. Once we explore that question carefully, the mystery begins to dissolve, revealing the graceful mechanics behind what our eyes can't immediately see. Think of it this way. When you say the Earth spins, you're describing how it turns once every 24 hours on an invisible line called its axis, an imaginary pole that runs from the North Pole to the South Pole. That spin gives us day and night. At the same time, Earth is also moving around the Sun, completing one full orbit every 365 days. Those are two separate motions happening simultaneously, rotation and revolution. One is a spin on its own center, the other is a journey around something else. Both are real, both constant, and both define how we experience time and motion. Now apply that same thinking to the moon. It too moves in two ways at once. It turns on its own axis, that's rotation, and it travels around Earth, that's revolution. The problem is that our senses aren't designed to separate those two movements easily when they're synchronized. So the question isn't, does the moon spin? The real question is, how does it spin in relation to its orbit? The subtle relationship between those two motions, its rotation and its revolution, is what creates the illusion that it doesn't move at all. Let's try a simple thought experiment to feel this more clearly. Imagine you're holding a small ball in your hand, representing the moon. Now, slowly walk in a circle around a lamp or candle in the center, that's Earth. As you move around the lamp, try to keep one side of the ball always facing the light. To do that, you'll notice your wrist must turn little by little. By the time you complete one full circle, you've turned the ball once on its axis. Without realizing it, you've just mimicked the moon's motion, one rotation for every revolution. If you had simply walked around without turning your wrist, the ball would show all sides to the light. That's what would happen if the moon didn't spin. But since it does turn just enough to keep one side facing us, we only ever see that same half. That's the key realization. Spinning doesn't have to mean obvious, visible turning. It can be perfectly balanced with another motion so the two cancel each other's appearance from a specific viewpoint. The moon spins, but it does so at exactly the right pace to match its journey around Earth. Its face toward us never changes, not because it's motionless, but because its spin is synchronized with its orbit. The same side always points our way, but it's constantly moving through space, turning smoothly, quietly, with mathematical precision. This brings us to an important philosophical point, one that astronomers and physicists often love to emphasize. Motion is relative. Whether something seems to spin depends entirely on your point of view. From Earth's surface, the moon looks still because our perspective is tied to our planet's position. But if you were to hover far above the solar system and watch from a stationary point in space, you'd see the moon constantly rotating, keeping pace with its path around Earth. From that vantage point, there's no illusion at all. The moon's rotation becomes obvious, just slower and more graceful than we imagine. It's almost poetic, isn't it? What looks like stillness from one perspective is revealed as motion from another. The moon's steady gaze toward Earth isn't a sign of lifelessness, but of harmony, a perfect balance between two forms of motion that, when seen together, create the appearance of calm. And this is where our question deepens further, because to fully understand this elegant balance, we must define those two words, rotation and revolution, not just in casual terms, but with scientific clarity. Only then can we uncover the secret mechanism that keeps the moon's face locked toward us, as if enchanted by gravity itself. To truly understand the moon's behavior, that quiet illusion that keeps one face turned toward Earth, we first need to get our vocabulary straight. Two words lie at the heart of this mystery: rotation and revolution. They sound similar, and in everyday conversation, people often mix them up. But in astronomy, they describe two very different kinds of motion, and confusing one for the other is exactly why so many people believe the moon doesn't spin. Once you see the distinction clearly, it's like a light turning on in a dark room. Suddenly, the moon's motion makes perfect logical sense. Let's start with rotation. Rotation is the act of an object turning around an internal axis, an imaginary line that runs through it, usually from pole to pole. When Earth rotates, for example, it spins on its axis once every 24 hours. That motion is what gives us day and night. Sunlight sweeps across the surface as our planet turns. Every planet in our solar system rotates, though they all do so at different speeds. Jupiter spins incredibly fast, completing one rotation in just about 10 hours, while Venus takes a painfully slow 243 Earth days to rotate once, and it even does so backwards compared to most planets. But no matter how fast or slow, that spin is rotation, turning around your own center. Now, revolution is a different type of motion altogether. Revolution describes an object traveling around another body in space, like the way Earth orbits around the Sun or the way the Moon orbits around Earth. When we say Earth completes one revolution around the Sun every 365 days, that means it makes one full trip around our star, following its elliptical path. The Moon, in turn, revolves around Earth every 27.3 days. That motion, the orbit, is revolution, not a spin, but a journey. It's essential to understand that both rotation and revolution can happen at the same time, and in most celestial systems, they do. Earth spins on its axis while it moves around the Sun. The Moon, too, spins on its axis while it orbits Earth. The complexity and the beauty arise when those two motions begin to interact in special ways. Sometimes they move independently, and sometimes, through gravitational influence and the slow sculpting power of time, they fall into perfect rhythm with each other. To make this difference intuitive, let's use a few simple analogies. Picture a spinning basketball on your finger. That's rotation. The ball is turning around its axis, showing you all its sides. Now, imagine you stop spinning the ball and instead walk in a big circle around your friend. You're still holding the ball, but now it's traveling around your friend instead of spinning. That's revolution.
Finally, if you walk in a circle around your friend but slowly twist your wrist so that the same side of the ball always faces your friend, you've combined rotation and revolution in a synchronized way. And that's exactly what the moon does with Earth. From a physics perspective, these two motions are distinct because they are measured differently. Rotation is measured as angular velocity around the body's own axis, how many degrees per hour or radians per second the object turns. Revolution, on the other hand, is measured as orbital period, how long it takes to make a complete circuit around another mass. The two can have different periods, or they can synchronize. When they synchronize, something special happens. One side of the rotating body always faces its companion, creating the illusion that it's not rotating at all. That phenomenon has a name, which we'll soon explore: tidal locking. But before we get there, it's worth pausing to think about what these two types of motion mean on a deeper level. Rotation represents individuality, an object moving around its own center, governed by its internal dynamics and momentum. Revolution represents relationship, the motion caused by gravitational connection to another body. Every planet, moon, and asteroid dances through the cosmos, performing both kinds of movement, balancing self-motion and orbit, independence and connection. The interplay between those forces is what creates the cosmic choreography we see across the universe. And here's the critical insight for our story. When people say the moon doesn't spin, they're only thinking in terms of revolution, its path around Earth, and forgetting about rotation, its spin around its own axis. They see it moving through the sky and assume that because the same face is always turned toward us, it must not be turning at all. But the moment we apply the proper definitions, the moment we separate those two motions, the illusion disappears. We realize that not only is it revolving, but it's also rotating, and doing so in perfect harmony with its orbit. You could say that the moon is locked in a kind of eternal duet. Its rotation and revolution so perfectly balanced that one motion hides the other from our eyes. This balance didn't happen by chance. It's the result of billions of years of gravitational interaction, a long, slow dance between Earth and its companion that gradually sculpted their motions into perfect sync. And so if we want to move beyond misunderstanding and see the moon's motion for what it truly is, we need to apply these terms carefully. Rotation is spinning on one's axis, revolution is orbiting something else. The moon does both. It spins on its axis once every 27.3 days and revolves around Earth in exactly the same time. That's why we always see the same face. It's the perfect demonstration of how the right combination of rotation and revolution can create the illusion of stillness so convincing it fooled humanity for millennia. But now that we've defined our terms, it's time to apply them, to take what we know about rotation and revolution and see exactly how the moon performs both motions at once. Because understanding the definitions is one thing, but seeing how they work together, how this balance plays out in real celestial mechanics, is where the story of the moon's motion becomes truly mesmerizing. Now that we understand the difference between rotation and revolution, we can finally apply those ideas to the moon and reveal what's really happening up there. When you look at that glowing orb in the night sky, you're not just seeing an object drifting through space, you're watching two intricate motions working together in perfect harmony. The moon rotates on its own axis, just as Earth does, but at the same time, it revolves around Earth. These two motions are happening simultaneously, and here's the fascinating part. They're synchronized so precisely that one hides the other from our perspective. That synchronization is the reason we always see the same lunar face gazing back at us. Let's break this down step by step, starting with the moon's rotation. The moon completes one full spin on its axis roughly every 27.3 Earth days. If you were standing on the moon's surface, it would take that long for the distant stars to make a complete circle around your sky. During that time, you'd experience a very long day and night cycle, about 2 weeks of sunlight followed by 2 weeks of darkness. The moon is rotating, but because it does so slowly, the change would be almost imperceptible without careful observation. Now consider the moon's revolution, its journey around Earth. It takes the moon the same 27.3 days to make one complete orbit around our planet. That means that as the moon spins once,
It also travels once around Earth. The two motions match perfectly. Because they're synchronized, the same side of the moon always faces Earth, while the far side remains hidden from direct view. From our vantage point, it appears that the moon is not spinning at all. Yet, from a universal perspective, it is performing a slow, deliberate pirouette through space. You can visualize this elegantly with a simple demonstration. Take a coin or any small round object and hold it at arm's length. Imagine that your head represents Earth and the coin is the moon. Now walk in a circle around yourself, keeping one side of the coin always facing your eyes. As you complete your circle, notice something. The coin has turned once around its own axis. You didn't consciously spin it, but to keep one side facing you, it had to rotate exactly one time during its orbit. That's exactly what the moon does. It spins once for every orbit it makes, one rotation per revolution. And this locked motion keeps its near side always pointed toward Earth. The synchronization between these two motions isn't coincidental. It's the outcome of billions of years of gravitational interaction between Earth and the moon. Long ago, the moon likely spun much faster, turning multiple times for each orbit. But over immense spans of time, Earth's gravity tugged on the moon unevenly, the near side experiencing a slightly stronger pull than the far side. These tiny tugs created friction inside the moon, slowly bleeding away rotational energy until its spin rate matched its orbital rate. Once those two motions aligned, the gravitational forces reached equilibrium. From that point onward, the moon remained locked, rotating and revolving in sync, eternally showing one hemisphere to Earth. When you think about it, this synchronization is like a cosmic balancing act. The moon is continuously moving, yet to us it appears still. If the moon didn't rotate at all, its surface would present all of its sides over the course of an orbit, like a spinning wheel seen from the side. We would see the entire lunar globe, piece by piece, across a month. But because its rotation and revolution are timed perfectly, we don't. Instead, we see the same face, night after night, the same familiar pattern of light and shadow that ancient people once gazed upon thousands of years ago. It's a brilliant illusion, a celestial magic trick performed by gravity. The moon is turning, but because it turns exactly once as it orbits Earth, the turning is invisible from our perspective. This is why for so long humanity assumed it didn't spin. It's a bit like walking in a circle while keeping your eyes locked on a single point. Your body is constantly turning, but because your gaze never shifts, it feels like you're facing the same direction. And this perfect synchronization isn't unique to the moon. It's actually a common outcome in celestial mechanics. Many moons throughout our solar system share this same behavior. Pluto and its moon Charon are tidally locked to each other, each always showing the same face to the other. Jupiter's moons, like Io and Europa, are also locked in similar ways. In fact, once you start looking, you realize that this dance of synchronized motion is one of the universe's favorite rhythms. It's nature's way of conserving energy and achieving stability through the subtle pull of gravity over eons. If you could step back and watch the Earth-Moon system from deep space, you would see something extraordinary. The moon moving around Earth, always keeping its same face toward it, like a dancer orbiting a partner without ever breaking eye contact. From that cosmic vantage point, the moon's rotation is clear. A smooth, elegant spin that happens so slowly and perfectly in step with its orbit that to any observer on Earth, the dance seems frozen in time. This perfect timing between rotation and revolution is known as synchronous rotation, and it's the natural endpoint of gravitational interaction between two close celestial bodies. The moon has achieved it. It's locked into a rhythm so stable it has persisted for billions of years. Understanding this is the key to seeing past the illusion. The moon's unchanging face isn't a sign of stillness, it's the signature of motion perfectly balanced, rotation and revolution performing in seamless harmony. And now that we've seen how the moon's two motions align so precisely, it's time to name this elegant phenomenon and explore what causes it. Because this synchronization, this exact matching of spin and orbit, has a scientific name and a remarkable story behind it.
one that reveals how gravity molds the motion of worlds over unimaginable timescales. What we've just described, that perfect balancing act where the moon spins once for every orbit it makes around Earth, has a scientific name. It's synchronous rotation. It's a phenomenon that astronomers also call tidal locking, and it's one of the most elegant examples of gravity's long, patient power to shape the movements of celestial bodies. It sounds almost poetic, but it's rooted in physics. Tidal locking means that the moon's rotation period, the time it takes to spin once on its own axis, is exactly equal to its orbital period, the time it takes to travel once around Earth. Because these two periods are the same, the moon always keeps the same face toward us, like a dancer turning just fast enough to maintain eye contact with her partner no matter how she moves. Let's think about what this really means in terms of motion. If the moon were rotating faster, different portions of its surface would slowly come into view as it orbited Earth. If it were rotating more slowly, we'd see the far side gradually drift into sight as the near side moved away. But because the rotation rate and the orbital rate are perfectly synchronized, those effects cancel out completely. The result, one hemisphere, the near side, is locked toward Earth and the far side remains hidden from direct view. From our vantage point, it appears that the moon is not spinning at all. Yet from a universal perspective, it is performing a slow, deliberate pirouette through space. This synchronization isn't just a coincidence. It's the product of tidal forces, the gravitational stretching and squeezing that occur when two bodies exert uneven gravitational pulls on each other. Just as the moon's gravity raises tides in Earth's oceans, Earth's gravity once raised immense solid tides on the moon itself. Billions of years ago, when the moon was newly formed and much closer to Earth, it likely spun much faster. But Earth's gravity pulled harder on the side of the moon that was facing it, creating a bulge, a slight elongation, like a stretched rubber ball. Because the moon wasn't yet synchronized, this bulge didn't line up perfectly with Earth. It lagged slightly as the moon spun. That misalignment created torque, a subtle gravitational twist. Over immense timescales, that twisting force acted like a cosmic brake, gradually slowing the moon's spin. As the moon's spin rate slowed, the bulge slowly moved into alignment with Earth's gravitational pull. Once the moon's spin rate matched its orbital period, the torque disappeared. The system reached equilibrium, and from that point onward, the moon became tidally locked, eternally showing one hemisphere to its parent planet. It's a quiet, invisible process that takes eons, but it's incredibly powerful. You can think of it as gravity's way of taming motion. Every time the moon rotated a little too fast, Earth's gravity pulled back on it, draining a bit of its rotational energy. That lost energy turned into heat deep within the moon's crust, subtly warming it as the spin slowed. Eventually, after countless millions of years, the rotation settled into perfect sync with its orbit, and the energy exchanged stopped. The moon, now locked, continued its eternal, graceful dance, rotating and revolving in harmony. The same side always facing Earth, the balance finally achieved.
Tidal locking isn't unique to the moon. In fact, it's a universal outcome of gravitational relationships between close bodies. Mercury, for instance, is partially locked to the sun. It completes 3 rotations for every 2 revolutions, a 3-to-2 resonance. Pluto and its largest moon, Charon, are so close in mass that they are mutually tidally locked, forever showing the same faces to each other. Even many of Jupiter's and Saturn's moons are tidally locked, always turning the same side toward their giant hosts. It's as if the universe prefers this state of symmetry, a kind of gravitational peace treaty between 2 orbiting worlds. From Earth, we experience this tidal locking as a kind of cosmic constancy. When you step outside on a clear night and gaze at the moon, you are looking at the same surface that every human who has ever lived has seen. The same craters, the same plains, the same pattern of light and dark. For billions of years, that view hasn't changed. It's as if the moon has chosen to hold one expression forever, a celestial face frozen in time. But from a wider perspective, the moon is not still at all. It's turning smoothly and continuously, always keeping pace with its orbit around us. If you could speed up time, Compress thousands of years into seconds, you would see the moon's motion as a steady, rhythmic spin. You'd watch it orbit Earth, spinning once per trip, locked in perfect rhythm. From space, it would look like a slow dance, a silver sphere circling Earth while always keeping one hemisphere pointed inward. That's synchronous rotation in motion. Simple, steady, and profoundly elegant. This synchronization also helps explain why the moon's orientation has remained stable for so long. The gravitational locking acts like an invisible tether, keeping it from tumbling or rotating unpredictably. It ensures that the moon's spin remains constant and that the balance between rotation and revolution is preserved. Without tidal locking, the moon might rotate at varying speeds or orientations, but with it, everything is aligned, predictable, and harmonious. In many ways, tidal locking is the cosmic equivalent of resonance in music. When two notes resonate perfectly, they produce a stable tone that doesn't waver. The same principle applies to celestial motion. Once the moon's spin resonates with its orbit, the system becomes stable, locked in a natural rhythm. It's not just a mechanical balance, it's an expression of the deeper harmony that runs through the fabric of the cosmos. Gravity, time, and motion weave together until chaos settles into order, until a spinning world falls into step with its path around another. This delicate balance, the one that keeps the moon's rotation period exactly matched with its orbital period, is one of the reasons the moon has remained such a steadfast companion in our sky. Every phase, from crescent to full and back again, is a result of this stable geometry. The light may change, the shadows may shift, but the face itself never turns away. That constancy, that quiet synchronization, is what we call tidal locking, the perfect harmony between spin and orbit that creates the illusion of stillness while concealing a slow, graceful rotation underneath. And now that we understand what tidal locking truly means, we can explore just how precise this synchronization really is. Because when we start talking about numbers, about how long it actually takes for the moon to complete a rotation and an orbit, we begin to see just how exact and astonishing this cosmic balance really is. When we begin to attach real numbers to the moon's motion, the sheer precision of this cosmic dance becomes even more astonishing. The moon completes both its rotation on its axis and its revolution around Earth in roughly 27.3 days. That single number, 27.3, defines one of the most elegant examples of synchronization in our entire solar system. It's not a rough coincidence or an approximate rhythm. It's a perfect match, refined by billions of years of gravitational interaction between our planet and its companion. Every 27.3 Earth days, the moon has turned once on its own axis, and in exactly that same time, it has traveled all the way around Earth, returning to the same position in space relative to the stars. Let's take a closer look at what those numbers really represent. Astronomers actually describe this period as the sidereal month, which measures the moon's orbit relative to the background stars. In that span of about 27 days, 7 hours, and 43 minutes, the moon rotates exactly one time on its axis. No more, no less. Because the two periods are identical, the same hemisphere always faces Earth. To us, this synchronization feels eternal, unchanging, as though the moon were a fixed object painted onto the night sky. But those numbers reveal that there's motion beneath that stillness, a slow, methodical turn happening right before our eyes, just too subtle for our senses to notice. It's important to remember that there's also another way of measuring the moon's cycle, one we're more familiar with, the synodic month, which lasts about 29.5 days. That's the period from one full moon to the next. The difference between 27.3 and 29.5 days comes from Earth's own movement around the sun. As Earth orbits the sun, the moon has to travel a little farther to line up with the sun again and complete its familiar phase cycle. But when we talk about the moon's true rotation and orbital synchronization, the number we care about is 27.3. That's the heartbeat of its motion, the perfect match that keeps the near side forever facing us. Think for a moment about how extraordinary that is. The moon is a sphere, nearly 3,500 kilometers in diameter, orbiting over 380,000 kilometers away from Earth, and yet its spin and its orbit are so precisely tuned that the same face has remained oriented toward us for billions of years. There's no visible drift, no slow reveal of new terrain. The synchronization is so stable that the same craters ancient humans saw, Tycho, Copernicus, Mare Tranquillitatis, are the same ones we see tonight, unchanged by time or perspective. That level of balance feels almost intentional, that it's purely the product of physics,
the long-term result of tidal forces evening out the moon's energy until the system found perfect equilibrium. If we were to observe the moon from far above the solar system, watching it complete orbit after orbit, we'd see that this 27.3-day rhythm governs its every motion. Each rotation aligns seamlessly with its revolution. In that time, the moon travels about 2.4 million kilometers around Earth, spinning just once during the entire journey. It's as if the moon has found the perfect tempo, not too fast, not too slow, locked in step with its path through space.
What makes this even more fascinating is that this number, 27.3 days, is also a reflection of the delicate gravitational relationship between Earth and the moon. It didn't start that way. In its early history, the moon was much closer to Earth, and its orbit was shorter and faster. Over time, the tidal interaction between them caused the moon to drift slowly outward, while its rotation rate gradually decreased. Eventually, the two periods matched, and the system reached the steady state we see today. Even now, that process isn't entirely over. The moon continues to drift away from Earth by about 3.8 centimeters each year, but its rotation and revolution remain perfectly synchronized. That's how strong and enduring this gravitational lock is. The precision of this balance also shows how delicate celestial mechanics can be. If the moon's rotation were even slightly faster or slower, we would notice the far side shifting into view over long stretches of time. But it doesn't. The match is exact enough that the moon's orientation has stayed consistent through all of human history, through the rise and fall of civilizations, through the evolution of species, and likely for billions of years to come. To think that a single number, 27.3, encapsulates all of that motion and all of that stillness at once is deeply humbling. It's a number that carries the weight of cosmic patience, a reminder that the universe finds balance not through sudden action, but through slow, persistent forces acting over unimaginable timescales. Even if we could somehow stand on the moon and watch Earth hanging in the sky, we'd see this synchronization in action. The Earth would appear to hover in almost the same spot above the lunar horizon, barely moving. From some locations on the moon, Earth would never rise or set at all. It would simply hang there, slowly rotating on its axis, showing its changing continents and clouds. That apparent stillness, the Earth fixed in the lunar sky, is a direct consequence of the moon's 27.3-day lockstep spin. To a lunar observer, the synchronization isn't an illusion. It's reality. So when we say it takes 27.3 days for the moon to rotate once and exactly 27.3 days to orbit Earth once, we're not just quoting statistics. We're describing one of nature's most perfect harmonies. It's the steady beat of the Earth-Moon relationship, a gravitational duet so precise that it creates the illusion of eternal stillness. And from that stillness emerges one of the most profound insights about the cosmos. That motion, when balanced perfectly, can become invisible. Now that we've explored the timing, the numbers that prove the moon's rotation and revolution are identical, we can begin to explore the consequence of that synchronization. What happens when two motions align so perfectly? What does this balance create in the night sky? And the answer is one of the most beautiful illusions in astronomy. The reason we always see the same face of the moon, even though it is spinning all along. Because the moon's rotation and revolution take exactly the same amount of time, 27.3 days, the result is a breathtaking illusion of stillness. From our perspective, here on Earth, the moon seems frozen, always showing us the same face. The dark blotches of ancient lava plains, the bright scars of impact craters, the familiar pattern that forms the so-called man in the moon, they never shift or drift. It's as if the moon has turned its gaze toward us and decided never to look away. Yet that impression of calm, of a celestial body holding perfectly still, hides a continuous graceful motion. The moon is turning. It's rotating steadily, but it does so in step with its journey around our planet, completing one full spin for every orbit. If you were to watch the moon from far out in space, away from Earth's surface, you would see this clearly. Against the background of distant stars, the moon is rotating on its axis. It's spinning, but it's also circling Earth, and those two motions are matched like the gears of a cosmic clock.
The same face that looks toward us sweeps through space, turning once per orbit, keeping its orientation locked toward Earth while the rest of the sky drifts around it. The far side, invisible from our planet, is not hiding motionlessly. It's simply facing away during the dance, moving through the same rhythm as the side we know. You can picture it easily with a simple movement of your own body. Imagine standing in the center of a room facing a friend who stays still while you walk slowly around them. To keep eye contact the entire time, you have to keep turning your body bit by bit as you go. By the time you've walked a full circle, you've also spun once. If you hadn't rotated at all, your back would be facing your friend halfway through your orbit. The moon behaves exactly that way. It's always looking at Earth, and the only way to do that is to rotate once for every revolution. The synchronization is perfect, so perfect that from our limited point of view, the motion cancels itself out. This locked rhythm creates the illusion that the moon isn't spinning, but it also explains why we never see the far side. The face we know so well is permanently turned toward us because the timing between spin and orbit is exact. Every time the moon completes one orbit, it's also completed one rotation. Every crater and plane on the near side has been staring at Earth since long before life emerged on our planet. The far side, by contrast, has been perpetually turned outward, invisible to human eyes until spacecraft finally revealed it in the mid-20th century.
This matching of periods also means that from the moon's surface, Earth's behavior looks completely different than how we see the moon from here. If you stood on the near side of the moon, Earth would appear almost motionless in the sky. It would hang there, large and luminous, slowly spinning on its own axis but never rising or setting. The stars would drift past, the sun would rise and set, but Earth would stay fixed, an unchanging presence above the horizon. On the far side, however, you would never even see Earth at all. To a lunar traveler, that would be a world with no blue planet in the sky, only blackness and stars. This striking contrast, Earth forever visible from one hemisphere and forever absent from the other, is the direct result of the moon's synchronized motion. The equal timing of rotation and revolution also has subtle effects that extend far beyond the visual illusion. It helps stabilize the orientation of the moon's orbit, reducing chaotic wobbling and keeping the system balanced. The gravitational grip that enforces this rhythm acts like a constant reminder that motion in space is relational. The moon's spin doesn't exist in isolation. It's shaped by Earth's pull, just as Earth's own rotation is gradually affected by the moon's tug on our oceans. Every moment, the two bodies influence each other, bound by invisible threads of gravity that maintain this perfect timing. It's remarkable to think that such an equilibrium didn't exist at the beginning. When the moon first formed, it likely spun much faster, turning several times during a single orbit. Over immense spans of time, friction within the moon caused by Earth's tidal pull slowed its spin. Eventually, the periods matched exactly, and the system settled into the synchronized state we see today. Once that balance was achieved, the forces that had been slowing the moon's rotation ceased to have a significant effect. The dance reached its steady tempo, and it has remained in rhythm for billions of years. This matching of periods also adds a sense of cosmic poetry to what we see in the sky. The moon's stillness is not the absence of motion. It's motion so balanced that it appears serene. The symmetry is perfect enough to trick human perception, but fragile enough that we can measure its tiny variations. Even now, scientists can detect minute wobbles, called librations, that let us glimpse slightly beyond the edge of the visible hemisphere. Those small shifts are reminders that the moon's motion is real, ongoing, and subtly complex. But overall, the illusion holds. The near side always faces us because the moon's spin and orbit are in perfect step. So, the next time you look up at the moon, remember that what appears frozen in place is actually turning in time with Earth's pull. The same craters, the same shadow basins, the same silent mountains you see tonight are all part of a rotating world,
performing a measured ancient dance that keeps its rhythm so precisely that it deceives our eyes. That equality of motion, the matching of a 27.3-day rotation and a 27.3-day orbit, is the secret behind the moon's unwavering gaze, the quiet mechanism that makes one side of the moon our eternal companion and the other an unseen mystery. The misconception that the moon doesn't spin is one of those enduring ideas that seems so obvious that even after hearing the explanation, many people struggle to let it go. You look up at the night sky, see that same unchanging phase, and your brain insists it must not be rotating. But this is the fascinating part. The moon is absolutely spinning. It's just doing so in a way that perfectly hides its spin from us. It turns once every 27.3 days, matching its orbit around Earth step for step, so the two motions cancel out visually. The illusion is so convincing that even though the moon is constantly rotating, it looks like it's simply gliding around Earth, staring back at us with that same tranquil expression. To make this concept feel more tangible, imagine you're on a merry-go-round, holding a camera that's always pointed toward one fixed point on the ground, say a tree. As you go around, you constantly twist your body to keep the tree in view. If you were filmed from above, you would clearly see yourself spinning. But to anyone sitting next to you on the ride, it would look as though you weren't turning at all, because your orientation to the tree never changes. That's the exact kind of optical trick the moon plays on us. It's turning just enough to keep its gaze fixed on Earth, and in doing so, it hides its own motion perfectly. This misconception persists because human perception is trained to associate rotation with obvious visual change. When a ball spins, we expect to see all its sides in motion. When Earth rotates, we experience sunrise and sunset. But the moon's rotation is synchronized with its orbit, so the visual cues our brains rely on never appear. The moon doesn't seem to spin because its rotation is always in harmony with its orbit, one motion constantly compensating for the other. The result is an illusion so elegant it deceived humanity for millennia. Even in the age of telescopes, this misunderstanding endured. Early astronomers, relying on naked eye observations, naturally assumed the moon was motionless. Its face never shifted, its features never rotated into or out of view, so they concluded it must be fixed. Only through careful mathematical modeling and centuries of accumulated observation did scientists begin to understand the subtle truth that the moon's rotation is not absent, but synchronized. Galileo and later astronomers like Cassini demonstrated that if the moon truly did not rotate, every side of it would eventually become visible as it orbited Earth. The fact that we only ever see one side proves it's spinning. Ironically, the moon's apparent stillness is the very evidence of its rotation. You can even test this yourself with something as simple as a coffee mug. Hold the mug in front of you, the handle representing one side of the moon, the side facing Earth. Now slowly move the mug in a circle around your body, but keep the handle always pointed towards your chest. You'll quickly realize that to maintain that orientation, you have to keep turning your wrist. By the time the mug has completed one orbit around you, it has also completed one full rotation. That's what's happening in space every single month. The moon is rotating, but in perfect synchrony with its orbit. Its handle, or near side, always points toward Earth. The idea that the moon doesn't spin also gives rise to several smaller misconceptions, one of which is that the far side is dark, as if it never sees sunlight. In reality, the far side receives just as much sunlight as the side we see. It's only dark to us because it's out of sight. This confusion stems from the same root error, the assumption that the moon is fixed in space rather than rotating. Once we understand that the moon spins, the picture changes entirely. Both sides experience day and night, both are lit by the sun in turn, and both are part of a dynamic rotating world. There's something deeply poetic about how this works. The moon's slow, steady spin is a reminder that motion doesn't always announce itself with spectacle. Sometimes it hides in balance. The moon rotates at exactly the rate needed to maintain its eternal orientation toward Earth, and the synchronization makes it appear utterly still. It's a cosmic lesson in perspective, the kind of paradox that only the universe could invent. A world that is both rotating and seemingly motionless at the same time.
To drive the point home, consider what would happen if the moon suddenly stopped rotating altogether. Imagine freezing its spin while it continues orbiting Earth. Over the course of a month, we would start to see different portions of its surface come into view. The familiar face of the moon would drift away, replaced by new craters and plains that have never faced us before. Eventually, we'd see the entire surface of the moon, one side at a time. The only reason that doesn't happen, the only reason we don't see that shifting view, is because the moon does rotate, just enough to keep its near side perfectly aligned with Earth's position in the sky. It's this precise mathematical balance, one spin per orbit, that sustains the illusion. And that illusion is powerful. For thousands of years, it shaped myths, inspired poetry, and led even early scientists to wrong conclusions. Only with the tools of modern observation and physics could humanity finally break through that veil and recognize the truth. The moon's stillness is an exquisite trick of timing. So the next time someone says the moon doesn't spin, you can smile and tell them the truth. It spins constantly, but it spins in rhythm with its orbit, like a dancer turning gracefully in time with her partner. The same face we see tonight has been turning through space all along, slowly, deliberately, in perfect harmony with the path that carries it around our world. What we mistake for stillness is actually one of the most precise and enduring motions in the solar system. And now that the misconception has been cleared up, the next question naturally follows. How did this perfect synchronization come to be? Was the moon always locked in this slow, rhythmic motion, or did something happen in its ancient past to bring it into alignment? To find that answer, we must journey back billions of years, to the time when the moon's dance with Earth was still wild, when gravity was sculpting its spin into the perfect balance we see today. To understand how the moon came to move in such perfect harmony with Earth, how it ended up rotating at exactly the same rate that it orbits, we have to travel back in time, billions of years, to the chaotic beginnings of the Earth-Moon system. In those early days, the moon was not the calm, synchronized companion we know today. It was a restless, rapidly spinning world whirling on its axis far faster than it revolved around our planet. When it first formed, likely from the debris left behind after a colossal impact between the young Earth and a Mars-sized body known as Theia, the moon was molten, close, and spinning with incredible speed. Its face changed constantly. No side was permanent. It had not yet been captured by Earth's gravitational rhythm. But even then, a subtle force was beginning to take hold, a cosmic tug-of-war that would gradually shape the moon's destiny. The culprit was gravity, specifically the immense gravitational pull that Earth exerted on its smaller companion. Gravity doesn't just attract, it distorts. Because the moon is not a perfect sphere, Earth's gravity stretched it slightly, pulling its mass into a small bulge, one facing Earth and another on the opposite side. As the moon rotated, those bulges shifted back and forth, constantly trying to realign with Earth's gravitational pull. This created a continuous tug, a kind of invisible friction that worked like a brake on the moon's spin. Over immense stretches of time, that braking effect began to slow the moon's rotation. Each time the moon turned, the gravitational pull from Earth twisted those tidal bulges slightly out of line, producing internal friction within the moon's rocky structure. That friction converted rotational energy into heat, energy that was then lost to space. Slowly, almost imperceptibly, the moon's rotation rate decreased. What began as a fast spin, perhaps lasting only a few hours per rotation, lengthened to days, then weeks, until eventually it matched its orbital period around Earth. Once the two periods synchronized,
the tidal bulges stopped shifting back and forth. The system had reached a stable equilibrium. The moon had become tidally locked. It's almost poetic to imagine that process. A young, glowing moon spinning rapidly under Earth's watchful gravity, slowly surrendering its speed, yielding to the rhythm of its larger partner. The slowing wasn't a sudden event. It unfolded over millions upon millions of years. Each turn of the moon brought a tiny loss of energy, an infinitesimal change in speed, until the balance point was reached, one rotation per orbit. When that happened, the tidal bulges lined up perfectly with Earth. The internal friction subsided, and the moon settled into the tranquil dance we witness today. This story isn't unique to our moon. The same gravitational braking that slowed it down is a universal process throughout the cosmos. Anywhere you have two bodies, one massive, one smaller, tidal forces can act to slow the smaller body's rotation and lock it into a synchronized spin. It's the reason many of the moons in our solar system are tidally locked to their planets. For example, Jupiter's Galilean moons, Io, Europa, Ganymede, and Callisto, all keep one face toward the giant planet. Saturn's Titan does the same. Over time, gravity sculpts motion into balance. Back in the early days of the Earth-Moon system, this process also had consequences for Earth itself. Just as Earth's gravity raised tides on the moon, the moon's gravity raised tides on Earth, in our oceans and crust. Those tides acted as a kind of feedback mechanism. As the moon's rotation slowed, Earth's own rotation began to feel the counter effect. The energy lost by the moon's spin didn't disappear completely. It was transferred, causing the moon to drift slowly away from Earth. Even today, that outward drift continues at a rate of about 3.8 centimeters per year. It's a slow but constant reminder of the dynamic relationship that shaped both worlds. In a sense, Earth and the moon have been partners in a long gravitational conversation. Early on, the moon's rapid spin made it the more energetic of the two. Earth's gravity gradually pulled that energy out of it, slowing its rotation while pushing it farther away. Over time, the moon's rotation period stretched until it matched its orbital period exactly. The two became synchronized, like a pair of dancers who, after a long struggle to match steps, finally move in perfect unison. Once that synchronization was achieved, the moon's face stopped changing. The system had found its natural rhythm, one that's so stable it has lasted for billions of years. This tidal locking process also left subtle marks on the moon's structure. The side that faces Earth is slightly different in composition and thickness from the far side. The near side has more maria, dark volcanic plains formed from ancient lava flows, while the far side is more heavily cratered and mountainous. These differences likely formed as the moon cooled and settled under Earth's gravitational influence. It's as if even the moon's geology bears the signature of this long gravitational dance. If you could speed up time and watch the history of the Earth-Moon system unfold and fast forward, it would look like an intricate slow-motion ballet. The moon would appear to whirl quickly at first, its spin fast and independent. Then, as millions of years pass in moments, you'd see that spin gradually decelerate. You'd notice the bulges twisting under Earth's pole, the moon's rotation slowing, until finally it locks into step, one rotation per orbit. From that moment on, one hemisphere of the moon would always face Earth, its features frozen in our view. The rest of its motion, its steady spin, would continue unseen, perfectly hidden within the balance it had achieved. This process reveals something profound about the universe itself. Over long timescales, gravity creates order out of chaos. The moon began as a fast-spinning fragment of a violent impact, but gravity patiently worked upon it until it found perfect harmony. That slow sculpting, over billions of years, transformed a molten, tumbling world into the steady, synchronized companion we see tonight, a world locked forever in a cosmic embrace. And now that the misconception has been cleared up, the next natural question arises. What was the exact mechanism that made this happen? What kind of energy exchange or frictional process was powerful enough to alter the spin of a celestial body? The answer lies in something called tidal friction, the subtle but persistent force that drove this transformation and still influences both Earth and the Moon even today. Tidal friction, the quiet, invisible force that brought the Moon into its perfect lockstep with Earth, is one of the most fascinating and powerful processes in celestial mechanics. It's not dramatic like a collision or an explosion. It's slow, patient, and relentless, sculpting motion over eons with the steady persistence of gravity itself. To understand how it works, imagine that the Moon is not a perfectly solid, unyielding sphere, but a body with some internal flexibility. In its early molten or semi-molten state, Earth's gravity tugged on the Moon unevenly, stretching it slightly and raising what we might call tides. Not tides of water, but tides of rock.
Even though the Moon doesn't have oceans, its interior could still bulge and deform under the pull of Earth's gravity. Wherever Earth's gravity was strongest, it drew the lunar material slightly outward, forming a small elongation, a bulge, pointing roughly toward Earth. On the opposite side of the Moon, another bulge formed due to the centrifugal force of the Moon's rotation and orbit. So at any given time, there were two tidal bulges on the Moon, one facing Earth and one facing away. But here's where the story becomes truly interesting. When the Moon was rotating faster than it orbited, those bulges couldn't stay perfectly aligned with Earth's gravitational pull. The Moon's spin carried them slightly ahead of the Earth-Moon line, twisting them just out of position. Now, this misalignment created a torque, a twisting force, that constantly acted against the Moon's rotation. Earth's gravity tugged on those off-center bulges, trying to realign them. Each time it did, friction within the Moon's interior converted some of that rotational energy into heat. Over countless orbits, that tiny continuous torque acted as a brake, draining energy from the Moon's spin and turning it into internal warmth. Bit by bit, orbit by orbit, the Moon's rotation slowed. This process is what we call tidal friction, and it's one of the most subtle yet transformative forces in astrophysics. It doesn't just affect the Moon, it operates everywhere in the universe where two bodies interact gravitationally and one has any flexibility at all. On the Moon, tidal friction gradually synchronized its spin with its orbit. Once the rotation period matched the orbital period, the bulges lined up perfectly with Earth, and the torque disappeared. The system reached equilibrium. From that moment onward, there was no longer any twisting or friction. The Moon was tidally locked, one hemisphere forever facing Earth, one forever turned away. You can think of this process like a kind of cosmic braking system, one that uses gravity as both the driver and the brake. Imagine spinning a rubber ball while holding it close to a powerful magnet that slightly distorts its shape. The magnet's pull would keep tugging on the stretched part of the ball, resisting its spin. Over time, the ball would slow down until it was rotating just fast enough that the stretched part always faced the magnet. That's exactly what happened to the Moon, except instead of a magnet, it was Earth's immense gravitational pull, and instead of seconds, it took billions of years. Interestingly, as its energy was dissipated inside the Moon, it produced heat. In its early history, that heat may have contributed to keeping parts of the Moon's interior molten for longer than it otherwise would have been. So in a sense, Earth's gravitational pull didn't just shape the Moon's motion, it helped shape its geology too. The tides that once stretched and flexed its crust left behind faint traces of internal restructuring, shaping the way the Moon cooled and solidified. The gentle but persistent kneading of tidal friction was one of the great unseen forces that made the Moon what it is. And tidal friction didn't only affect the Moon. It works both ways. As Earth pulled on the Moon and slowed its spin, the Moon's gravitational pull raised tides on Earth as well. Tides in our oceans and even in Earth's crust. Those tides move slightly ahead of the line between Earth and the Moon, due to Earth's faster rotation. As a result, Earth's tides exert a small forward pull on the Moon, transferring angular momentum from Earth rotation into the Moon's orbit. This causes the Moon to drift gradually away from Earth, inch by inch every year. Even today, this process continues at a measurable rate of about 3.8 centimeters per year, verified by laser reflectors left on the lunar surface by Apollo astronauts. That's tidal friction at work, still quietly reshaping the relationship between our two worlds. What makes tidal friction so profound is how it demonstrates the elegance of gravitational balance. It's not a sudden or violent process, but a slow dialogue between motion and energy, between spin and orbit. Earth gravity sculpted the moon's spin through nothing more than gentle, persistent tugging, an invisible hand guiding it into synchrony. The moon's rapid early rotation gave way to stillness relative to us, not through loss, but through balance. The energy didn't vanish, it was merely transformed, converted into heat, into orbital distance, into the subtle geometry of a gravitational partnership that has lasted for eons. In that sense, tidal friction tells a story of patience, of how motion can be refined into harmony through time. It's a reminder that the universe doesn't rush to order. It drifts there, step by step, guided by natural laws that need no intervention. Every moment that the moon orbits Earth today, that balance remains in place, the legacy of a process so ancient and gradual that it defies our sense of time. What we see as stillness in the sky is, in truth, the culmination of billions of years of motion that has settled into perfect symmetry. And as extraordinary as that might seem, the moon story is not unique. Tidal friction has shaped countless moons across the solar system and beyond into similar states of synchronization. The moon's lock rotation is just one example of a universal pattern written across the cosmos. So to see how truly natural this phenomenon is, we need only look outward to the many other moons orbiting the giant planets, each one a reflection of the same timeless gravitational choreography. Tidal locking, as it turns out, is not some rare cosmic coincidence reserved for our moon alone. It's one of the most common and natural outcomes in the universe. The same gravitational process that slowed the moon's spin and synchronized it with its orbit around Earth has repeated itself countless times across the solar system. Nearly every large moon orbiting a planet is tidally locked, showing the same face to its parent world, just as our moon does to us. It's a universal pattern, a kind of gravitational fingerprint that emerges whenever a smaller body orbits a larger one for long enough.
Take Jupiter, for instance. The giant planet's four largest moons, Io, Europa, Ganymede, and Callisto, are all tidally locked. These worlds are vastly different in size, composition, and distance from Jupiter, yet each one spins once per orbit, keeping one hemisphere permanently turned toward their immense host. Io, the most volcanically active body in the solar system, experiences tremendous gravitational stretching from Jupiter's immense pull, generating enough internal heat to drive continuous volcanic eruptions. Europa, with its smooth, icy crust and hidden subsurface ocean, also bears the marks of tidal forces, its surface constantly flexing and cracking under Jupiter's gravity. Ganymede, the largest moon in the solar system, and Callisto, an ancient cratered relic, both follow the same rhythm, locked in step, turning once for every orbit. It's the same story around Saturn. Titan, Saturn's largest moon, and the only one with a thick atmosphere, is tidally locked to its parent planet. From Titan's surface, Saturn would hang motionless in the sky, immense and golden, while the stars wheeled around it. Mimas, Enceladus, Tethys, Dione, Rhea, all tidally locked as well. Each one faces Saturn with one hemisphere, always showing the same craters, ridges, and plains to their planet, while their far sides remain unseen except to spacecraft. The same process that froze our moon's gaze upon Earth has sculpted a whole family of moons into similar postures around their giant hosts. This tidal locking extends even to distant Uranus and Neptune. Miranda, Ariel, Umbriel, Titania, and Oberon, all Uranian moons, are locked. Triton, Neptune's largest moon, follows suit, orbiting in a retrograde direction but still keeping one face toward its planet. No matter where we look, the pattern repeats. It's as if the cosmos prefers symmetry, a natural tendency for orbits and rotations to fall into balance over time. What's striking is that tidal locking doesn't only happen between planets and moons. The same principle can occur between stars and binary systems, or between planets and their stars. Astronomers now believe that many exoplanets, especially those orbiting very close to their suns, are tidally locked as well. In such systems, one side of the planet always bakes under perpetual daylight, while the other remains an endless night. These eyeball planets, as they're sometimes called, might look like giant cosmic yin-yangs, one hemisphere glowing hot and bright, the other frozen and dark. Even there, far beyond our solar system, tidal friction has sculpted motion into harmony. It's remarkable to realize that what we see when we look at the moon, that serene, unchanging face, is not an anomaly, but a glimpse of a universal law in action. Gravity, when given enough time, seeks equilibrium. The same slow dance between spin and orbit that unfolded between Earth and the moon has been repeated over and over again across space. Every tidally locked moon is a record of time, a sign that billions of years have passed, that energy has been exchanged, that a once wild spin has been tamed into stability. In the case of Jupiter's moons, the story of tidal locking becomes even more complex and fascinating. Io, for example, doesn't just experience tidal locking, it also endures tidal heating. As it orbits Jupiter, it is pulled not only by the planet, but also by its neighboring moons, Europa and Ganymede, which keep its orbit slightly elliptical through gravitational resonances. That elliptical orbit means the tidal forces Io experiences are constantly changing, stretching and squeezing the moon rhythmically. The result? Immense heat generated within its interior, powering volcanic eruptions that can spew plumes hundreds of kilometers high. It's the same basic process. Tidal forces and friction, but taken to an extreme. What slows the moon into gentle balance around Earth fuels Io's fiery surface around Jupiter. Europa, too, owes its hidden ocean to tidal forces. The same gravitational interactions that locked its rotation also need its icy crust, keeping the interior warm enough for liquid water to exist beneath the surface. Without tidal friction, Europa might have frozen solid eons ago. Instead, it remains geologically active, potentially even habitable beneath its miles of ice. Ganymede's magnetic field, Titan's thick atmosphere, Triton's nitrogen geysers, all are shaped in one way or another by the same process that synchronized our moon's spin. This pattern tells us something profound about the nature of time and motion in the universe. Given enough time and the persistent pull of gravity, motion tends towards stability. Spin slows, orbits align, and systems fall into synchronized rhythms. What looks like stillness, like our moon's constant face, is actually the endpoint of motion refined by time. Tidal locking is not a frozen state, but a balance reached through continuous energy exchange. Even now, that forces are still active, maintaining that balance, adjusting it ever so slightly as orbits shift and spins evolve. If we could look at the solar system through the lens of tidal interactions, we would see a vast web of relationships. Every moon, every planet, every star, subtly tugging on its companions, exchanging energy, shaping rotation, and defining motion. The moon's relationship with Earth is only one thread in that immense cosmic tapestry. The same harmony that binds the moon to us binds countless other worlds to their hosts, creating a universe full of quiet, synchronized dancers orbiting in endless grace.
So when we gaze at the moon and think of it as our special companion, we're seeing not just an exception, but a reflection of a deeper universal truth, that gravity loves balance. Across the cosmos, worlds turn in orbit and rhythm, their motions sculpted by the same subtle hand that once slowed our moon's spin. Tidal locking is gravity's signature of time. The mark it leaves when it has had enough patience to smooth chaos into order. And yet, even in this balance, there's motion. Small imperfections, gentle oscillations, tiny variations that let us glimpse just a little more of these locked worlds than we should. In the case of our moon, that variation has a name, a delicate wobble called libration, which allows us to see a bit beyond the edge of the familiar lunar face, offering us fleeting glimpses of the hidden far side. Even though the moon is tidally locked, always keeping the same face turned toward Earth, A careful observer might notice something curious. Over time, we can actually see a little more than just one half of it. In fact, we can see about 59% of the moon's total surface, a little more than half, thanks to a subtle and graceful phenomenon known as libration. Libration is, in essence, a gentle wobble in the moon's orientation, a small oscillation that lets us peek slightly beyond the edges of its near side. It's as if the moon, while holding its steady gaze on Earth, sways just enough to reveal a bit more of its hidden face, giving us fleeting glimpses of the terrain that usually lies out of view. This wobble is not a single motion, but the result of several overlapping effects, each caused by different aspects of the moon's orbit and tilt. The first and most significant is libration in longitude, which arises because the moon's orbit around Earth is not a perfect circle. It's an ellipse. That means the moon's orbital speed changes slightly as it moves along its path. When it's closer to Earth, at perigee, it moves faster. When it's farther away, at apogee, it moves slower. But the moon's rotation, its spin on its axis, stays constant. This mismatch between its constant spin and its changing orbital speed causes the moon to appear to rock back and forth a little from our point of view. Over the course of its orbit, we can peer around the eastern and western edges of the moon, revealing about 8 degrees of extra surface on each side. Then there's libration in latitude, which comes from the fact that the moon's axis of rotation is tilted slightly by about 6.7 degrees relative to the plane of its orbit around Earth. Because of this tilt, sometimes we can see a little over its north pole and at other times a little below its south pole. It's similar to how Earth's axial tilt gives us changing seasons, except that in the moon's case, the effect is a slow nodding motion that lets us peek alternately over the top and bottom of the lunar sphere. A third type, called diurnal libration, happens because we observe the moon from different points on Earth's surface as our planet rotates. When the moon is rising, we're viewing it from one angle on Earth's curvature. When it's setting, we're seeing it from another. This daily shift in perspective adds a small apparent wobble of about 1 degree. It's subtle, but when combined with the other forms of libration, it contributes to the extra slivers of the lunar surface we can observe over time. When you add up all these small wobbles in longitude, in latitude, and the daily diurnal shift, the result is that we can see roughly 9 degrees beyond the moon's nominal edge on all sides. That means that over time, careful observers on Earth can view about 59% of the moon's surface, even though no single moment ever reveals more than half. The moon's face seems fixed, yet across days and weeks, it breathes slightly, rocking gently in its orbit like a slow pendulum, exposing new details along its margins. It's a subtle dance, a reminder that even in perfect balance, nothing in the cosmos is truly still. If you've ever looked through a telescope and noticed that the shape or orientation of certain lunar craters near the limb, the moon's edge, seems to shift slightly from night to night, you've seen libration in action. Sometimes the great crater Grimaldi, near the moon's western edge, is more visible. At other times, it almost disappears. Features along the eastern rim, like Mare Smithae or Mare Marginis, come into view briefly only to vanish days later. These changes aren't due to clouds, shadows, or illusion. They're the visible evidence of the moon's gentle wobble as it moves through its orbit. What's particularly beautiful about libration is that it feels almost like the moon is alive, subtly interacting with us, moving just enough to remind us that it's a dynamic world, not a static ornament. It's as if the moon allows us brief glimpses past the curtain, teasing us with the mystery of its far side. For centuries, those fleeting views sparked deep curiosity. Early astronomers wondered, what lies just beyond the edge? What landscapes remain forever hidden from Earth's gaze? Before the age of spaceflight, libration was humanity's only way to glimpse even a hint of the moon's concealed hemisphere. The moon's slight wobble also offers astronomers valuable opportunities. By carefully mapping the regions revealed through libration, scientists were able to extend our knowledge of the lunar surface long before spacecraft arrived.
Early selenographers, lunar cartographers, like Johann Schroeder and Johann Madler in the 18th and 19th centuries, used libration to chart these boundary zones with painstaking precision. Their maps were works of both science and art, showing the limits of the known moon and hinting at the worlds just out of sight. Only centuries later, when space probes finally circled the moon, did we discover how small those glimpses were compared to the vast and alien far side. Libration is, in many ways, the moon's quiet confession. It reveals just enough to prove that the unsigned side exists, but not enough to show it in full. It's the cosmic equivalent of a whisper, a subtle nod that reminds us that our perspective is never complete. And it's also a sign of the moon's true nature, perfectly balanced, yet not rigid, locked in orbit, yet still in subtle motion. Even now, precise instruments measure these wobbles with astonishing accuracy. Lunar orbiters and laser reflectors confirm that the moon's librations are predictable, mathematical, and rhythmic. They are the small imperfections that make the system more human, more relatable. The tiny deviations that remind us that even celestial harmony includes a little movement, a little asymmetry. And this gentle swaying of the moon helps us transition naturally into another common source of confusion, one that stems directly from the way we perceive its motion. Many people still refer to the moon's hidden hemisphere as the dark side, imagining it as a place shrouded in perpetual shadow. But that, too, is a misunderstanding born of our Earth-centered point of view. The far side is not always dark at all. It experiences sunlight and night just as the side we see does. The only difference is that from our vantage point, we can never watch it happen.
The phrase, the dark side of the moon, has echoed through popular culture for decades, from song lyrics to science fiction, but it's one of the most persistent misconceptions in all of astronomy. The truth is that there is no dark side of the moon, at least not in the sense that one half lives forever in darkness. Both sides of the moon experience day and night, each bathed in sunlight for about 2 weeks and then cloaked in darkness for the next 2. The real distinction isn't between light and dark, it's between what we can see from Earth and what we can't. The hidden hemisphere should be called what it truly is, the far side of the moon, the side that always faces away from us, not the side that never sees the sun. This confusion stems from how perfectly the moon's rotation and revolution are synchronized. Because it turns once for every orbit, the same face always looks toward Earth. From our perspective, that means we never see the other side. But from the sun's perspective, the situation is entirely different. Over the course of its orbit, every part of the moon, near side and far side alike, takes turns facing the sun. When we see a full moon in our sky, its near side is fully illuminated by sunlight, meaning the far side is experiencing night. 2 weeks later, when we see a new moon, the phase when it vanishes from our view, the far side is in full daylight while the near side is dark. The far side has its own cycle of lunar days and nights, just offset from ours by half a period. Imagine standing on the far side of the moon. You'd watch the sun rise slowly over the horizon, crawl across the sky for 2 Earth weeks, then sink into a long, cold lunar night. From your vantage point, Earth would never rise. It would always remain below the horizon, but the stars and the sun would move in their long, patient arcs. You'd see the sunlight sweep across craters and mountains, illuminating terrain no human eyes on Earth could ever witness directly. There would be brilliant, blazing days and pitch-black nights, just like anywhere else on the moon. The term dark side endures partly because the far side remained a mystery for so long. Before the space age, no one had ever seen it. Telescopes could show us only the familiar near side with its smooth lunar maria and distinctive patterns. The far side was invisible, forever turned away, and so people naturally imagined it as a place of perpetual darkness. It became a symbol of mystery, of the unknown, of what hides just out of sight. But scientifically, it was simply the side we hadn't yet observed. When the first images of the far side were finally captured in 1959 by the Soviet spacecraft Luna 3, they completely upended expectations. The far side was not an identical twin of the near side. It was rougher, more heavily cratered, and lacked the broad, dark plains, the seas or maria, that dominate the moon's face visible from Earth.
Instead, it was a scarred and ancient landscape, shaped by eons of impacts and far less volcanic activity. This revelation gave astronomers new insights into the moon's history and the forces that shaped it. It also confirmed, beyond any doubt, that while one side is hidden from us, it's certainly not dark. The difference in appearance between the near and far sides has a fascinating geological explanation. The moon's crust is thicker on the far side, roughly 50 kilometers thicker than on the near side, which means that when molten rock once welled up from the interior during its early volcanic period, it couldn't easily breach the surface there. On the near side, the thinner crust allowed lava to flood giant impact basins, forming the dark basaltic plains we call Maria. That's why the moon's familiar face looks smoother and darker in places, while the far side remains rugged and bright. The contrast is a geological record of ancient asymmetry, and a reminder that what we don't see can be very different from what we do. Understanding that both sides receive sunlight also helps clarify why lunar eclipses and phases happen as they do. The moon's phases, crescent, half, full, are simply the changing patterns of sunlight and shadow we observe as it moves around Earth. During a full moon, we're looking directly at the sunlit near side. During a new moon, that same near side is dark because sunlight is falling entirely on the far side. During the intervening phases, we see varying amounts of illumination. None of these changes come from the moon producing or losing its own light, it's just the sunlight shifting across its surface. Every part of the moon participates in this cycle, alternating between day and night every 29.5 Earth days. So, if you were standing on the far side during one of our full moons, you'd see something quite opposite, a new Earth. Our planet would be hidden in the glare of the sun, invisible against the light. And 2 weeks later, as the moon grew dark in our sky, you'd see a full Earth rising over your horizon, a magnificent blue and white globe suspended in the black sky, larger and brighter than any star. It would never move from its position, but it would slowly change phase just as the moon does from our viewpoint. This poetic symmetry, Earth's phases seen from the moon and the moon's phases seen from Earth, ties both worlds together in a perfect gravitational duet. The idea of the dark side has persisted partly because it feels evocative, mysterious, even romantic. It's easy to imagine that the hidden phase of our nearest neighbor must conceal secrets, and in a way it does. But those secrets are not of eternal shadow, they are stories written in ancient stone, in craters and ridges shaped by billions of years of cosmic history. The far side isn't a place of perpetual darkness, it's a place that experiences sunlight just as fully as the near side, but sunlight that no human eye on Earth can witness directly. It's illuminated every month, shining silently in the void, unseen from our planet, but glowing all the same. Even now, orbiting spacecraft and robotic probes continue to study that hidden hemisphere in exquisite detail. They've mapped every mountain and basin, revealing that the far side, once thought to be a realm of shadow, is in fact dazzlingly bright and rich in geological complexity. It's a powerful reminder that darkness in astronomy rarely means absence of light. It more often means absence of knowledge. What was once called the dark side has turned out to be one of the most enlightening regions in the study of the moon. And that revelation, that the far side is bright, real, and wonderfully different, paved the way for one of humanity's greatest moments of discovery, when spacecraft first captured its image and showed us what had been hidden for all of human history. Those first photographs didn't just satisfy curiosity, they forever changed our understanding of the moon, transforming the phrase dark side into a scientific correction. For thousands of years, the far side of the moon was one of humanity's greatest mysteries, an entire half of our nearest celestial neighbor hidden from view, never seen by any telescope or eye on Earth. Ancient astronomers could map every crater and plain on the moon's visible face with remarkable precision, but the hemisphere facing away remained purely a realm of imagination. Then, in October of 1959, the Soviet spacecraft Luna 3 achieved what no human or machine had ever done before. It traveled far enough around the moon to photograph its far side. Those blurry, grainy black and white images, beamed back across space, marked one of the most extraordinary moments in the history of exploration, the moment when humanity finally saw the hidden half of the moon.
The images from Luna 3 were primitive by today's standards, captured with early film technology and transmitted through radio signals. Yet they revealed something stunning. The far side of the moon looked nothing like the side we see from Earth. Gone were the vast, dark maria, the smooth plains of ancient basalt that dominate the near side and form the face of the moon as we know it. Instead, the far side was almost entirely covered in craters, mountains, and rugged highlands. Only a few small dark patches, such as Mare Moscovensi and Tsiolkovsky crater, broke the otherwise bright, heavily cratered terrain. It was as if the moon had two personalities, one face smooth and familiar, the other rough and ancient, scarred by time. Scientists were astonished. For centuries, many had assumed the moon's far side would look roughly the same as its near side, perhaps with similar maria or recognizable patterns. But Luna 3's photographs shattered that assumption. The asymmetry begged for explanation. Why would one hemisphere be so different from the other? Over time, lunar scientists discovered that this contrast is deeply rooted in the moon's internal structure. The crust on the far side is much thicker, about 50 kilometers more than that of the near side. Because of this thicker crust, molten rock from the moon's interior could not easily erupt onto the far side surface during its volcanic period billions of years ago. On the near side, the thinner crust allowed lava to flow into impact basins, forming the dark plains we now call the lunar maria. The far side, denied this resurfacing, remained pitted and ancient, preserving the record of impacts from the early solar system. Luna 3's discovery was just the beginning. In the 1960s, a series of follow-up missions from both the Soviet Union and the United States expanded our view. The Soviet Zond and Luna probes captured higher quality images, while NASA's lunar orbiter missions, launched between 1966 and 1967, provided thousands of detailed photographs, mapping nearly the entire moon, both near and far sides, in preparation for the Apollo landings. These missions confirmed what Luna 3 had shown. The far side is a rugged, mountainous region covered in craters, vastly different in texture and geology from the smoother near side. When astronauts aboard Apollo 8 orbited the moon in December 1968, they became the first humans to lay eyes directly on the far side. As their spacecraft emerged from behind the moon, their radio connection with Earth temporarily went silent, a haunting period of radio blackout as they passed through the shadowed hemisphere. Astronaut Bill Anders described the far side as a vast expanse of battered, desolate terrain with none of the large, dark features so familiar on the side that faces Earth. The experience left a lasting impression on the crew and on humanity as a whole. For the first time, people had not only seen, but also traveled behind the moon, witnessing with their own eyes the secret face that had eluded human vision for millennia. Subsequent missions built upon these early revelations with ever-increasing precision. NASA's Clementine mission in 1994 provided the first global digital map of the moon, revealing the far side in unprecedented detail. In 2009, the Lunar Orbiter mission, LRO, began orbiting the moon, capturing images so sharp that scientists could study the texture of individual boulders and crater walls. These modern datasets showed that the far side surface is older and more heavily bombarded, containing features that date back to the earliest era of the solar system, a natural time capsule of cosmic history. Even more recently, in 2019, China's Chang'e 4 mission made history by becoming the first spacecraft to land on the far side of the moon. It touched down in the von Karman crater, within the vast South Pole Aitken Basin, one of the largest and oldest impact structures in the solar system. Because the far side is perpetually hidden from Earth's direct radio signals, the mission relied on a relay satellite, Kekchao, positioned beyond the moon to transmit communications. Chang'e 4 carried not only a lander, but also a small rover, U-22, which began exploring the surface, analyzing rocks, soil, and the local environment. This mission represented a new chapter in lunar exploration, humanity's first close-up look at the far side surface, achieved through a remarkable feat of engineering. What Chang'e 4 and other modern missions have revealed continues to refine our understanding. The far side is not just rougher, it's geologically unique.
it contains higher concentrations of certain materials like aluminum and thorium and fewer of the volcanic basalt flows that dominate the near side. The crust's extra thickness and the lower presence of radioactive elements suggest it cooled differently in the moon's early history. The contrast between hemispheres tells us that the moon's internal heat and composition were distributed unevenly, possibly influenced by Earth's gravitational pull during its early formation when both bodies were still molten. There's also the South Pole Aitken Basin itself, an immense scar nearly 2,500 kilometers wide and 13 kilometers deep, one of the largest known impact structures in the solar system. It dominates much of the far side's southern hemisphere and may hold key clues about the moon's interior. Scientists believe that studying this region could reveal rocks from deep beneath the lunar crust, perhaps even from the mantle. That's why upcoming missions, including NASA's Artemis program and future robotic explorers, are targeting this basin for exploration. The far side, once hidden from all human sight, has now become one of the most scientifically exciting frontiers. The transformation of our understanding of the far side is nothing short of profound. In just over 60 decades, it has gone from being a poetic symbol of mystery to one of the most well-mapped and studied celestial surfaces in our solar system. From Luna 3's ghostly images to Chang'e 4's panoramic color photographs, the journey represents humanity's relentless drive to unveil the unknown. What was once imagined as the dark side turned out to be a realm of revelation, a key to unlocking the moon's past and, by extension, the story of Earth and the early solar system itself. And as we learned more about why the far side looks the way it does, shaped by crustal differences, ancient impacts, and gravitational interplay, we also came to understand why it stays so perfectly oriented towards us. The moon's locked posture isn't random. It's maintained by the stabilizing grip of Earth's gravity, which holds it steady and keeps its orientation fixed. That gravitational partnership is the next piece of this celestial story. The reason the moon doesn't tumble or wobble wildly, but remains serenely balanced, its one familiar face turned towards us forever. The moon's calm and unwavering face that gazes down at Earth every night isn't just a coincidence. It's the product of a delicate gravitational balance that has lasted for billions of years. The reason the moon stays in such a stable orientation, always showing us the same side without tumbling or spinning erratically, lies in the persistent grip of Earth's gravity. This invisible force doesn't just keep the moon in orbit, it acts as a kind of cosmic anchor, holding the moon's orientation steady and preventing it from wobbling freely through space. It's as if the Earth and the moon are connected by an unseen tension, a gravitational handshake that locks them together in a synchronized embrace.
To understand this stability, we first have to think about how gravity works on a body that isn't perfectly symmetrical. The moon, despite appearing round and smooth from afar, is not a perfect sphere. It's slightly asymmetric, a little elongated, with its mass distributed unevenly. Its center of mass has shifted slightly toward Earth, about 2 kilometers off center. That subtle imbalance means one side, the near side, is slightly heavier or more gravitationally anchored than the other. When the moon rotates, Earth's gravity tugs a bit harder on that bulging side, pulling it back into alignment. Over time, this continuous gravitational interaction has acted like a restoring force, ensuring that the same hemisphere always faces Earth. Think of it like a pendulum, or a weight attached to a spring. If you pull it slightly to one side and let go, it swings back to its original position. The moon behaves in much the same way. Small deviations in its orientation are corrected by Earth's gravitational pull, which constantly nudges it back toward equilibrium. This is why, although the moon does exhibit slight oscillations, the librations we discussed earlier, it never flips over or changes its orientation dramatically. Its motion is stable, self-correcting, and bound by the subtle but powerful physics of gravitational potential. If the moon were perfectly spherical, this locking wouldn't be possible. A sphere has no preferred orientation. Gravity would pull equally on all sides, and the moon could spin freely without resistance. But because of its elongated shape and mass asymmetry, the gravitational force creates what's known as a torque, a twisting effect that resists rotation out of alignment. early in its history, before it became tidally locked, this torque acted like a brake. As the moon spun, the gravitational pull from Earth created small distortions or tidal bulges on its surface. These bulges were always slightly misaligned with Earth because of the moon's rotation, and that misalignment generated friction inside the moon. Over millions of years, that internal friction dissipated rotational energy as heat, slowing its spin until its rotation matched its orbital period exactly. Once the two periods synchronized, the torque vanished and the system settled into a stable, locked state, the one we see today. But stability doesn't mean total rigidity. The moon's orientation remains steady, yet it's not frozen. As the moon orbits Earth, it experiences small gravitational influences from other bodies, primarily the sun, that can slightly perturb its motion. These influences cause gentle rocking motions, or librations. But Earth's dominant gravitational pull keeps the moon from deviating too far. The result is a stable balance between motion and constraint, a system in which the moon moves gracefully without ever losing its synchronized posture. It's worth noting that this kind of gravitational locking isn't unique to our moon. It's a natural equilibrium that emerges in many celestial systems. But what makes the Earth-Moon pair so special is how long and stable this relationship has been. Computer models suggest that once tidal locking occurs, it tends to remain extremely stable for billions of years unless disrupted by a massive external event, such as a large impact or a significant shift in orbital dynamics. In the case of our moon, no such event has disturbed this harmony since the early ages of the solar system. The gravitational bond between Earth and Moon has persisted, unbroken, maintaining the same serene face through the entire history of life on our planet. This stability has had profound consequences, not only for the Moon itself, but also for Earth. The locked orientation of the Moon contributes to the stability of Earth's axial tilt, which in turn helps regulate our planet's climate over geological timescales. Without the Moon's steady gravitational influence, Earth's tilt could wobble chaotically, leading to extreme and unpredictable changes in climate. In a sense, the Moon's gravitational lock with Earth doesn't just keep its own face steady, it helps keep the rhythm of life on our planet stable as well. The physics of this law creates a kind of equilibrium zone. The Moon is constantly in a tug-of-war between inertia, which would carry it forward in a straight line, and gravity, which keeps pulling it toward Earth. The result is a precise orbital motion, a perpetual fall around Earth that never quite ends. Within that motion, the gravitational torque ensures that the Moon's heavier side always faces inward. It's a delicate interplay of forces, motion and stillness, push and pull, freedom and restraint. Over billions of years, those forces have settled into a kind of cosmic harmony, a steady rhythm that appears timeless from our perspective. One might wonder what would happen if this balance were disturbed. If, for example, a massive asteroid struck the Moon with enough force to slightly alter its rotation, Earth's gravity would once again begin the slow process of restoring synchronization. The torque would act as a brake, gradually re-establishing the locked orientation over millions of years. That's the beauty of this gravitational mechanism. It's self-correcting. The same forces that created the lock also ensure its persistence. From a more poetic viewpoint, Earth's gravity acts almost like a teacher to the Moon, guiding, correcting, keeping it in perfect rhythm. The two have been bound in this celestial relationship for most of the solar system's history, a relationship that defines both worlds. When you look up at the Moon and see that same familiar face, the Sea of Tranquility, the Ocean of Storms, the bright Tycho crater, you're witnessing the product of a gravitational dance so precise that it has endured for over 4 billion years without missing a beat. And yet, even with this incredible stability, many people still wonder, if the Moon truly spins, if it really rotates on its axis, then why can't we ever see the far side of it from Earth? Why does this synchronization result in such perfect alignment that one hemisphere remains hidden forever? The answer to that question brings us to one of the most elegant explanations in all of celestial mechanics: the relationship between one rotation per orbit and the unchanging face that defines our view of the Moon. It's one of the most natural questions anyone asks after learning that the Moon does spin. If it's rotating on its axis, then why can't we ever see the back of it?
At first glance, it feels contradictory. When we think of spinning, we picture an object turning and revealing all its sides, like a globe slowly rotating on a stand, or a dancer twirling in place. So how can the moon rotate without showing us its far side? The key lies in how perfectly its rotation matches its revolution, one spin for every orbit around Earth. It's this one-to-one synchronization that keeps the moon's far side perpetually out of view. Let's break this down in a way that's easy to visualize. Imagine holding a tennis ball in front of you, with one spot marked to represent a crater. Let's say that spot faces your nose. Now slowly walk around a chair, keeping that same spot on the ball always facing toward the chair's center. As you move around, you'll notice that you have to rotate your wrist a little at each step to keep the same side of the ball pointed inward. By the time you've made one full circle around the chair, the ball has also spun exactly once on its own axis. You've just performed the same motion the moon does, rotating once for every revolution. If you hadn't turned the ball at all, the marked spot would have ended up facing away from the chair halfway through your orbit. That's what would happen if the moon didn't rotate. In that case, as it orbited Earth, we'd see its entire surface over time. Every crater, every mountain, every hidden valley. But that's not what we observe. Instead, the same face always looks toward us, which means the moon must be rotating at just the right speed to keep that alignment constant. The apparent stillness is an illusion created by synchronous rotation, a perfect balance of spin and orbit. To see how this works numerically, remember the key figure. The moon takes about 27.3 days to complete one orbit around Earth, and it also takes 27.3 days to complete one rotation on its axis. These two motions, spinning and circling, occur together in harmony. So while it's turning relative to the background stars, it's also moving around Earth at the same pace. The result is that its orientation relative to us never changes. Every time the moon finishes one orbit, it has also spun exactly once, no more, no less. From our vantage point, this creates the illusion of stillness. We see the same features, the Sea of Tranquility, the Ocean of Storms, and the bright streaks of Tycho crater, always in the same places. The moon seems motionless, but if you could observe it from deep space, far enough away to watch its entire orbit, you'd see that it's turning smoothly, keeping one hemisphere pointed toward Earth at all times. Its rotation isn't absent, it's perfectly matched. This is a subtle point that can be tricky to grasp because our everyday experiences with rotation and orbit don't usually happen in such perfect sync. On Earth, for example, a full rotation, one day, takes 24 hours, but our revolution around the sun takes 365 days. That mismatch means we see the sun rise and set every day. But if Earth rotated exactly once for every orbit around the sun, one hemisphere would be locked in perpetual daylight, while the other would endure eternal night. A situation similar to how the moon is locked to Earth. So the reason we never see the back of the moon isn't because it's not spinning, it's because it spins just right. Its rotational period and its orbital period are in exact harmony. This synchronized movement means that for every degree it travels around Earth, it rotates 1 degree on its axis. Over the course of one lunar month, it completes both a full orbit and a full spin, ensuring the same side always faces us. There's an elegance to this motion that's easy to overlook. The moon's rotation is real, measurable, and smooth, not some frozen state, but a graceful, continuous dance that stays in step with its orbit. You could think of it like two dancers waltzing together. The moon is the partner who always faces the other dancer, Earth, turning perfectly as they move in a circle. To an outside observer, both dancers are in motion, but to the one they're facing, there's a constant connection, an unbroken gaze maintained through flawless timing. Astronauts who orbited the moon during the Apollo missions saw this dynamic firsthand. As their spacecraft looped around the moon, they passed into the moon's hidden hemisphere, the far side,
and for a short time, they lost radio contact with Earth. From their perspective, they saw the landscape Earth could never see: immense craters, rugged highlands, and vast basins, untouched by human eyes. Then, as they continued their orbit, the near side came back into view, and communication was restored. They were moving around the moon, not spinning it, but the view from Earth remained the same. The moon's rotation was keeping pace perfectly with its orbit, maintaining that eternal orientation. This also means that if you were standing on the near side of the moon and looked up at Earth, you'd see something just as astonishing. Earth would hang almost motionless in the lunar sky, never rising or setting. It might shift slightly due to the moon's libration, that small wobble we discussed earlier, but it would remain nearly fixed, always in the same spot, slowly turning on its own axis. From the far side, however, you would never see Earth at all. It would always remain below the horizon, forever hidden. So the reason we can't see the back of the moon isn't mysterious. It's the result of one of the most beautiful examples of gravitational precision in nature. The moon spins, yes, but in perfect synchrony with its orbit, keeping its face locked to Earth. This synchronization, once established billions of years ago through tidal forces and friction, has held steady ever since. It's not that the moon refuses to turn, it's that it turns exactly enough to stay aligned. And that alignment, this elegant balance between motion and stillness, leads naturally into one of the most poetic truths about our cosmic relationship with the moon. Its rotation and revolution are not in opposition, but in harmony, locked together in a dance so precise that it feels choreographed. The more we understand it, the more we see that what seems motionless is actually one of the universe's most exquisite examples of synchronized motion, a quiet cosmic harmony that has lasted for billions of years and will continue long after we are gone. There is something profoundly poetic about the way the moon moves, something that transcends the boundaries of pure science and drifts into the realm of art and music. The balance between its rotation and revolution is not just a mechanical coincidence. It's a form of cosmic harmony, a celestial rhythm so delicate and precise that it feels almost alive. When you think about it deeply, the moon and Earth are engaged in an eternal dance, one that has been playing out silently for billions of years. The moon's motion is not chaotic, not random, not hurried. It's patient, deliberate, graceful, like a dancer whose every step is perfectly timed to the music of gravity.
This synchronization, known as tidal locking, is one of the most elegant examples of nature's ability to find equilibrium. Through countless collisions, tides, and forces over eons, the moon gradually settled into a motion that conserves energy and maintains balance. It's as if the universe fine-tuned the system until it achieved a kind of serenity. Once the moon reached the point where its rotation period matched its orbital period, one spin for every trip around Earth, everything fell into perfect rhythm. From that moment, there was no longer any wasted motion, no conflict between forces. The rotation and revolution became one unified motion, each supporting the other, each sustained by the same gravitational thread. Think of it as a dance between partners who know each other so well that no misstep ever occurs. The moon turns, Earth pulls, and together they move in a precise, fluid cycle that repeats endlessly. To us, standing on the surface of our planet, it appears that the moon never changes. But that stillness is an illusion born of perfect timing. In truth, the moon's every movement is calculated, every rotation synchronized, every revolution guided by an ancient rhythm written into the laws of physics. It's like watching a pendulum swing in perfect tempo with a clock, an eternal metronome keeping time with the heartbeat of the Earth itself. This harmony doesn't just represent physical balance, it symbolizes the way the universe tends toward order through the passage of time. When celestial bodies interact through gravity, they exchange energy, adjust their motions, and eventually settle into stable configurations. It's a process that can take millions or billions of years, but the result is always elegant, a kind of natural choreography born out of chaos. The Earth-Moon system is one of the clearest examples of this universal pattern. What began as turbulence, a young, rapidly spinning moon bombarded by impacts and tidal stresses, slowly transformed into the serene, synchronized motion we see today. It's nature's way of finding peace through balance. If you could speed up time and watch the history of the Earth-Moon system unfold, it would look like a dance slowing into synchronization. At first, the moon would spin rapidly, its face constantly changing relative to Earth. But as Earth gravity pulled on its tidal bulges, friction within the moon would dissipate energy, gradually slowing its spin. The rotations would begin to line up with the orbit, the motions becoming smoother and more regular, until finally, the spin and orbit fell perfectly into step. From that moment onward, the dance became one of flawless symmetry. The same face, the same gaze held steady through the passage of eons. This balance is more than scientific, it's poetic in its consistency. The moon's still gaze upon Earth is a visual metaphor for constancy itself. No matter how fast Earth spins, no matter how much humanity changes, that same familiar face looks back at us every night. Every culture that has ever looked up at the sky, ancient Sumerians, Egyptians, Greeks, Chinese astronomers, has seen the same craters and seas, the same man in the moon. It's one of the few unchanging visual anchors in the entire human experience. And it all exists because of that perfect balance between rotation and revolution. In many ways, this cosmic harmony mirrors the rhythms of our own lives. Just as the moon found stability through balance, so too do living systems. From the beating of our hearts to the cycles of day and night, the turning of the seasons, the rise and fall of tides. These are all manifestations of synchronization, the universe's quiet way of creating structure from movement. The moon's motion is simply a grander, more enduring version of the same principle. It shows us that balance doesn't mean stillness, it means motion and harmony. Forces in opposition finding a rhythm that sustains both. What's even more fascinating is that this synchronized state is not fragile. It's remarkably stable, a dynamic equilibrium maintained by the very forces that created it. Earth's gravity continues to hold the moon in place, while the moon's pull on Earth creates our ocean tides, subtly influencing our planet's own rotation in return. There's a feedback loop at play, an ongoing exchange of energy that maintains this delicate balance. Over incredibly long timescales, Earth's rotation will continue to slow, and the moon will drift farther away, but the synchronization between them will persist, always adapting, always staying in step. If you could listen to the solar system the way a musician listens to an orchestra, the Earth and moon would be playing in perfect unison, two notes resonating at the same frequency. Their gravitational interaction produces a kind of silent rhythm, a cosmic duet that speaks in the language of motion. And it's not an isolated phenomenon. All throughout the universe, planets and moons, stars and satellites, binaries and systems large and small, engage in these same gravitational harmonies. The Earth-Moon pair is just our most intimate glimpse of it, our closest example of nature's drive towards symmetry. So, when you look up at the moon, you're not just seeing a lifeless sphere hanging in space. You're witnessing one of the purest expressions of cosmic order, a motion so precisely balanced that it appears still, a dance so perfect that it seems eternal. The moon's rotation and revolution are not two separate movements, but one single seamless act of balance. It's gravity's masterpiece, a silent, unbroken waltz that has lasted for over 4 billion years and will continue long after we are gone. This graceful balance naturally leads to an even deeper reflection. The synchronization between Earth and Moon isn't an isolated miracle. It's part of a much larger story, a universal tendency toward harmony that extends across the cosmos. From binary stars locked in mutual orbit to planets shepherded by their moons, the universe is full of these rhythmic pairings. Gravity, time, and motion weave together like notes in a grand symphony, and our moon's quiet, steady spin is just one beautiful chord in that vast composition. When we lift our eyes from the moon and look beyond it, past the confines of our own sky and out into the vastness of space, we begin to see that this graceful balance between rotation and revolution is not unique to our moon at all. It's part of a much grander design,
a universal truth written into the laws of motion and gravity. The same invisible hand that locked the moon to Earth has sculpted the motions of countless worlds across the cosmos. Gravity, though silent and unseen, is the great choreographer of the universe, the force that turns chaos into rhythm, randomness into order, and drifting dust into cosmic dances that can last for billions of years.
The moon's perfect synchronization with Earth is simply one node in this larger symphony. Everywhere we look, gravity shapes how celestial bodies move, interact, and evolve. It is the sculptor that molds the orbits of planets, the spin of moons, and the graceful spirals of galaxies. Every object that drifts through the cosmos, from tiny asteroids to massive stars, is following the same universal rule: to move in response to gravity's pull, trading energy for stability and often settling into patterns of harmony. The phenomenon of tidal locking, the very mechanism that keeps our moon's face turned toward us, is just one of gravity's many masterpieces. Take Jupiter, for instance. It's surrounded by a family of over 90 moons, and most of its larger ones, like Io, Europa, and Ganymede, are tidally locked to it, just as our moon is to Earth. Io, the innermost of Jupiter's major moons, experiences such intense tidal forces that its entire surface constantly flexes and shifts, generating enough heat through friction to power hundreds of active volcanoes, the most volcanically active world in the solar system. Europa, slightly farther out, is locked in the same way, with one hemisphere always facing Jupiter, its icy crust hiding a vast subsurface ocean kept warm by those same tidal forces. Gravity doesn't just organize these moons' motion, it breathes energy into them, drives their geology, and shapes their very potential for life. Move farther out still and you'll find Saturn's moon Enceladus, also tidally locked, also warmed by gravitational stretching. Its icy shell cracks and flexes as Saturn's gravity pulls and releases it, creating massive geysers that shoot water vapor hundreds of kilometers into space. Neptune's moon Triton, Pluto's moon Charon, even many of the small irregular satellites scattered throughout the solar system, all show signs of this same gravitational relationship. Wherever there is a dominant planet and a loyal moon, the music of gravity plays its familiar tune. Slow the spin, synchronize the orbit, establish balance. Over time, the rough motions of birth settle into graceful equilibrium. But this principle doesn't stop with moons and planets. The universe is filled with locked systems at every scale. Binary stars, for example, often become tidally locked to each other, spinning and orbiting in perfect unison. Some even share material between them, trading gas and energy in a celestial embrace that can last millions of years. In such systems, the same physical laws that govern our moon's motion dictate the entire dance. The forces that keep the moon's face toward Earth are the very same that align stars, shape galaxies, and orchestrate the motions of cosmic clusters. And when we look at the grandest scales, galaxies swirling in their majestic spirals, we see that gravity still rules. It is gravity that draws stars together into clusters, that pulls galaxies into collisions and mergers, that sculpts the filaments and voids of the cosmic web stretching across the universe. Every rotation of a galaxy, every orbit of a planet, every gentle pull between star and companion, all are expressions of gravity's creative power. It is the quiet artist of the cosmos, endlessly molding motion into form. What makes this realization so awe-inspiring is that the same physical law applies everywhere to everything. The same equation that describes the pull between Earth and Moon also governs the orbits of exoplanets hundreds of light years away. The same forces that synchronized our moon's spin and orbit shape the tides of distant alien oceans, the rotations of binary pulsars, and the steady spirals of entire galaxies. The patterns repeat, scaled up or down, yet always harmonious, always bound by gravity's invisible rhythm. And here's the truly profound part. Gravity doesn't just move things, it sculpts them. Over vast stretches of time, it refines motion the way a sculptor refines stone, carving away excess energy until only balance remains. Moons become tidally locked, planets settle into stable orbits, galaxies find their rotational equilibrium. everything drifts to a state of dynamic stability where forces balance and energy is minimized. It's as if the universe seeks peace through motion, finding serenity not in stillness, but in perfect, synchronized movement. When we realize this, the moon's behavior becomes more than a simple curiosity. It becomes a window into the deeper workings of the cosmos. That familiar, unchanging lunar face we see every night is a reminder that we're part of a vast, interconnected system governed by the same elegant laws. The same forces that keep the moon's rotation synchronized with its orbit are the ones that keep Earth bound to the sun orbiting the center of the Milky Way, and the Milky Way itself moving through the expanding universe. Everything is part of one grand gravitational ballet, infinite in scale, timeless in duration, and breathtakingly precise. Even the small irregularities, the tiny librations, the wobbles, and the occasional disruptions are part of this larger harmony. They show that while the universe tends to order, it never loses its dynamism. There's always motion, always change, always evolution. Yet within that movement, there's balance. The moon's synchronized spin is not a frozen state. It's a living equilibrium, a constant conversation between motion and stillness, energy and gravity, freedom and restraint. So when we look up at the moon and marvel at its still face, we're not just seeing our nearest neighbor, we're seeing the signature of gravity itself, the same creative force that builds and shapes everything in the cosmos. The moon's silent dance around Earth is a small echo of the universe's grander rhythm, a microcosm of the harmony that binds all things. And it's humbling to realize that this cosmic order doesn't just happen out there, it includes us. The same gravitational laws that govern the moon's synchronization also hold our feet to the ground, steer our planet through space, and define the passage of our days and nights. We are participants in this grand choreography, not separate observers. We live within the same rhythm that moves the moon. And as we begin to grasp this universal pattern, we arrive at the perfect moment to close the circle, to reflect on what this means for us here on Earth. The moon's timeless motion is not static. It's a lesson in balance, in grace, in the way the universe maintains order through constant motion. It's a cosmic mirror, reflecting back to us one simple truth, that harmony doesn't mean stillness, it means everything moving together in perfect time. And so after traveling through all these layers of understanding, from the illusion of stillness to the reality of motion, from the mechanics of tidal locking to the universal dance of gravity, we return to where we began, the moon, shining quietly in the night sky, forever turning the same face toward us. For countless generations, humanity has looked up at that silvery disk and felt both wonder and mystery. Ancient poets saw a watchful companion. Scientists saw a riddle waiting to be solved. And the answer, after all the equations and observations, is both simple and profound. The moon does spin, just perfectly in step with its orbit, in a rhythm so exact that it appears motionless. It's not frozen in space. It's moving constantly, gracefully, ceaselessly, turning once on its axis every time it travels once around Earth. This synchronization, so subtle and so complete, hides its rotation from our eyes. But the truth is there, written in its very motion. The moon's apparent stillness is a disguise for one of the most elegant dances in the universe. Its spin and orbit are intertwined, two halves of the same motion, locked together by gravity's quiet insistence that balance must be found.
Picture it, the moon gliding around our planet, not as a dead rock or a static lantern in the sky, but as a dancer caught in an endless waltz. It turns just enough to keep its gaze on us, the same face always illuminated by Earth's reflection, the same seas and craters watching our world spin below. There's something poetic about that, a kind of cosmic devotion, as though the moon has chosen to never look away. Of course, it's not choice that binds it, but physics. Yet somehow, the result feels deeply emotional. It's science that reads like poetry, motion that looks like stillness, order that arises from chaos. If you could watch from a distant point in space, far beyond Earth's orbit, you would see the full truth. The moon turning slowly, elegantly, spinning in perfect time with its path around our planet. you would see that what appears constant from our ground-bound perspective is actually alive with movement. Smooth, precise, eternal. One rotation per revolution, locked in step, forever maintaining that same steady gaze. It's a quiet choreography between two worlds, a gravitational duet that has lasted for billions of years and will continue for billions more. And when you realize this, when you truly understand that the moon is spinning, you begin to see motion itself differently. You realize that stillness can be an illusion, that harmony can exist in motion, and that balance is not about stopping, but about moving in rhythm. The moon teaches us that motion doesn't always look the way we expect it to. Sometimes the most perfect movement is the one that looks like none at all. That lesson extends far beyond the moon. It's written into the very nature of the universe. In the way planets orbit stars, stars revolve around galactic centers, and galaxies swirl in the vast dark fabric of space. Every motion is connected. Every orbit is part of a larger rhythm. Every gravitational pull a note in the cosmic symphony. The moon's spin is just one small measure in that infinite music, but it's one we can see with our own eyes every night from the surface of this spinning world. So, the next time you step outside on a clear night and look up, take a moment to really see it. That calm, glowing face you know so well, the one that has watched over human history from the dawn of time, is not staring stilly down. It is turning, gracefully, continuously, in perfect synchrony with its orbit around us. It's locked not in stillness, but in motion, a quiet, timeless dance choreographed by gravity itself. The moon does spin. It always has. It always will. But it spins in harmony with its journey, one rotation for every revolution. And that perfect synchronization keeps one face turned toward us forever. It's a cosmic heartbeat, steady and eternal, a reminder that even in the vast silence of space, there is rhythm, balance, and grace. And as you stand beneath that ancient light, remember this: what seems unchanging in the heavens is really a story of motion, of forces in balance, of gravity's subtle artistry, of time and energy intertwined. The moon's motion is a whisper from the universe itself, telling us that true harmony isn't about standing still, it's about moving together, perfectly in tune. That's the secret the moon has been showing us all along. Not a still companion, but a dancer in orbit, performing a silent waltz that has never missed a step. Its dance continues tonight, as it has for 4.5 billion years. A symbol of stability born from motion, of beauty born from balance. The moon spins, quietly, gracefully, a constant companion moving forever in step with the earth, keeping its face turned toward us in an endless, serene embrace. And that eternal motion disguised as stillness is one of the most beautiful truths in all the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.